All right, let's jump right in. Welcome to today's Explainer, where we're going to decode the fascinating, totally hidden language of computers. We're going to explore exactly how basic electronic switches, which, if you think about it, essentially just turn on and off, are somehow able to bridge the gap into the rich, complex human communication we see on our screens every single day. By the end of our time together, I promise you're going to see your devices in a completely different light. So, here's our quick roadmap for today. We'll be covering the language of zeros, doing math in binary, sizing up computer memory, hexadecimal, the human shortcut, BCD for exact accuracy, and finally, decoding text with ASCII and Unicode.
Let's start right at the foundation. Part 1, the language of zeros.
You know, beneath all those sleek interfaces and crazy high-def graphics, computers really only understand one single thing, and that's binary. It's a base 2 number system. Now, in our everyday lives, we use a base 10 or denary system, but computers rely on tiny electronic circuits that can only ever be in one of two states, either on or off. Because of that, they use a system based strictly on the values 0 and 1, and each individual digit in this system is known as a bit, which is literally just short for binary digit.
So how do those simple ones and zeros actually translate into meaningful numbers? Well, think of it like a grid of column weightings. Starting from the right, each column just doubles in value. It goes 1, 2, 4, 8, 16, and so on. Every time a 1 appears in a column, we just add that column's value to our running total. The zeros? We just ignore those. So if you were to add up columns for 128, 64, 32, 8, 4, and 2, you'd get a denary total of 238. It's an incredibly elegant system once it clicks.
Now, if you ever want to go the other way around and translate our everyday denary numbers into computer logic, there's actually a pretty cool step-by-step hack for that. It's called the successive division method. You literally just take your number and repeatedly divide it by 2, making sure to note the remainder each time. Once you hit 0, you just read those remainders from the bottom back to the top, and boom, you have your binary sequence. It's a fundamental trick every computer scientist learns early on. But that covers basic counting. How does a computer actually calculate things?
That brings us to part 2, doing math in binary.
So what happens when things go totally wrong in computer math? Picture this. Imagine we're trying to add the positive numbers 82 and 69, and we're using 8 bits to do it. The correct answer obviously should be 151. But here's the catch. In an 8-bit system using signed numbers, the maximum positive value we can actually represent is 127. So when the computer tries to run this calculation, the 1 spills over into the far left column. In this system, that far left column actually acts as a negative sign. We call this an overflow error. By trying to hold a number that's just too large for its allocated memory block, the computer spits out a completely nonsensical answer of negative 105.
This brings up a really crucial question. How on earth do computers deal with negative numbers in the first place? They can't exactly just write a minus sign on the circuitry. So computer scientists invented this brilliant mathematical trick called 2's complement. To represent a negative number, you take the positive version of the binary number and you invert every single digit. So all the 1s become zeros and the zeros become 1s. That part is known as 1's complement. Then you simply add 1 to the far right position. This ingenious little method allows the computer to process both addition and subtraction seamlessly using the exact same hardware. But as we start stacking all these bits into bytes, we run into a major scaling problem.
Let's look at part 3, sizing up computer memory.
Okay, be honest. Have you ever bought a new hard drive, plugged it in, and wondered why it magically has slightly less space than what was printed on the box? Well, here is the mystery solved. Hardware manufacturers typically use standard decimal prefixes, meaning a kilobyte is exactly 1,000 bytes. But remember, computers think in binary, so their prefixes are actually based on powers of 2. For a computer, a kilobyte is exactly 1,024 bytes. As we scale way up to megabytes and gigabytes, that tiny 24-byte discrepancy multiplies massively. And that creates a very noticeable gap between the decimal storage you paid for and the binary storage your operating system is actually reading. And that massive scale leads us right into a very practical problem. A modern hard drive holds trillions of bits. Trillions! Staring at endless walls of binary 1s and 0s is basically impossible for human readability. How on earth do developers manage this without going completely crazy?
That takes us to part 4, hexadecimal, the human shortcut.
Enter hexadecimal. This is a base 16 number system, and it is a total lifesaver for programmers everywhere. It uses the standard denary digits 0 through 9, but then it introduces the letters A through F to represent the numbers 10 through 15. Now, you might be wondering, why base 16? Well, it's because exactly 4 binary bits can represent up to 16 different values. This means we can perfectly compress a long, super unwieldy string of binary into a really compact, human-readable format. Instead of squinting at 4 separate ones and zeros, a programmer just reads a single letter or number.
Because it's just so incredibly efficient at compressing binary data for our eyes, you'll actually see hexadecimal used everywhere in the real world. When your laptop connects to Wi-Fi, it's identified by a MAC address written in hex. The modern internet relies on IPv6 routing, which uses hex. If you've ever built a website, you definitely know that HTML and CSS define colors using hex codes. It's also the absolute standard for reading low-level computer memory dumps and writing assembly language code. It's essentially the shorthand language of computer science.
But let's move on to part 5, BCD for exact accuracy.
Now, while hex is a fantastic shortcut for humans, some applications in the real world demand absolute, perfect exactness. And here's the thing, when you convert really large decimal numbers into binary, you can actually lose a tiny fraction of precision. To solve this, we use something called binary coded decimal, or BCD for short. Instead of trying to convert the whole massive number at once, BCD stores every single denary digit exactly as its own independent 4-bit binary code. So the number 3165 isn't calculated as one giant binary block. It's read exactly as a 3, a 1, a 6, and a 5 sitting side by side in memory.
So why does this matter to you? Well, BCD is absolutely crucial for your bank account because standard floating point binary math can cause microscopic rounding errors. If a bank's servers use standard binary, those tiny errors would compound over millions of transactions, and digital money would literally just disappear into the digital ether over time. No joke. BCD completely prevents this by locking down the exact decimal digits. It's also the standard for driving electronic calculator screens and digital clock displays, where every single digit needs to be completely isolated and accurate.
Okay, finally, part 6, decoding text with ASCII and Unicode.
So we've successfully conquered math, memory efficiency, and monetary accuracy. But what about language? How do we actually get text onto a screen? To do that, we use character sets like ASCII. ASCII is essentially just a giant lookup table that translates raw binary and hexadecimal values into human-readable characters. For example, the capital letter A is stored as the decimal value 65, which is 41 in hexadecimal. A lowercase a is 97. Even hitting the spacebar is recorded as the number 32. So whenever you type a message on your keyboard, you're actually rapidly firing these numerical codes straight to the processor.
But ASCII has a pretty fatal flaw. It originally only used 7 or 8 bits, meaning it could only handle a maximum of 256 unique combinations. That's totally fine for the standard English alphabet and a few control codes, but it's completely insufficient for our globalized world. That's exactly where Unicode steps in. Unicode takes this entire concept a massive step further. By utilizing up to 4 bytes or 32 bits per character, Unicode creates enough memory blocks to represent literally millions of unique characters. This is what allows a computer to flawlessly render every single alphabet, symbol, and emoji across all the languages of the world.
It's honestly mind-blowing when you take a step back and realize that every single high-definition video you watch, every text you send, and every secure bank transfer you make still relies entirely on these clever foundational hacks of ones and zeros. Understanding how these tiny electronic switches represent our entire digital world gives you a pretty powerful glimpse into the true nature of computing. But it also leaves us with a really exciting question. As our data scales into massive new tiers like Yobi Bytes, and as our global digital language continues to evolve, what new hidden representations will we have to invent next to bridge the ever-shrinking gap between human thought and the machine? Thank you so much for exploring the hidden language of computers with me today. Keep learning, and I'll catch you on the next Explainer.